And where is the mic?
Barely. ಗೊತ್ತಿಲ್ಲ ಕಾಪಿ ಆಗಿದೆ ಬಿಡಿ ಇಲ್ಲಿ ತೊಂದರೆ ಇಲ್ಲ.
Whatever it is that you will hit and list.
It's on.
This doesn't work.
This also works.
This works. Okay, good afternoon. Sorry for the delay in starting. It's my pleasure to welcome you to the Nobel Prize in Physics lecture of 2022. And it's been a tradition here that we speak about the Nobel Prize, and it's a matter of great joy for Raman Research Institute that the Nobel Prize this year was awarded to an area which is a key area of strength that our institute has in experimental efforts in quantum information and ion traps and and there are a lot of connections that our researchers have to the Nobel Prize winners and their groups, and it's certainly befitting that one of our faculty members give this talk. So I'm delighted that Urvashi Sinha, who's a professor at our institute, she heads a lab called Quantum Information and Computing, Quick Lab at RRI. And she has been recognized by Simon's Emmy Noether Fellowship at Perimeter Institute, Canada, and she is associate faculty member at IQC, University of Waterloo, and the Center for Quantum Information and Quantum Control, University of Toronto, Canada. Urvashi did her master's and PhD at Cambridge. So during her PhD, she worked on high temperature superconductivity, and during that period, she had the Gates Cambridge Scholarship and Nehru Shevnenin Scholarship during her master's. Her lab here works on cutting edge photonics, quantum information processing, and quantum computing. And she is amongst the leading researchers in the field, including some of our other colleagues here. And her scientific recognition includes Homi Bhabha Fellowship for 2017, 2018 ICTP, ICO, Galileo Leonardo Award in optics. She was also recognized as Asia's one of the top 100 scientists by Asian scientists for the year 2019. And the list goes on. She has been taking major initiatives in terms of connecting to the global community. So we recently have signed MOUs with Russian Quantum Institute, Quantum Center, and we hope that the team here with the leading researchers will also play a big role in India's growing aspirations to contribute and take some leadership roles in the global quest for quantum supremacy in some sense, or quantum applications to look at the other side. I will not say anything more, but it's really a pleasure that this is a field which has been recognized. This is a very active field, and I'm glad that there are many of you here to listen to this, and many of you have joined online to our live stream. And I'll look forward to an exciting talk from Urvashi. Urvashi.
So, am I audible at the back? Yeah. So, thanks a lot, Tarun, for this very kind introduction. And of course, thanks again to the director and the directorate for inviting me to present this talk here today. It is a huge honor to be able to talk to you about seminal work that has been done by living legends in our field. So, you know, it is a privilege that I get to do this for the next hour or so. The Nobel Prize in Physics 2022 has been awarded to Alan Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. Right? So this Nobel Prize to me is significant for two reasons. Of course, this is my personal view. And the first one is in fact a personal reason. You know, this is the field that my lab here and we are passionate about. We're working in this field. So for us, as well as the entire photonic quantum science and technologies community, this is a very thrilling moment that, you know, these recognitions have been given to these three stalwarts in our field. The second reason is, of course, hidden in this citation here. You know, this prize has been given not just for the contributions to the fundamental science aspect, which of course is very crucial, you know, experiments with entangled photons, violation of Bell inequalities. There is a lot of fundamental physics and fundamental science associated with this. But it has also been given for pioneering quantum information science. So this means that this is given not only to the fundamental science, but also to the applied technologies. And this in fact makes it very special, because it is not, you know, in some sense, you know, some work that has been done several decades ago and it has been recognized now. It's not just that. It's about where we are today. We call ourselves, you know, members of the, you know, second quantum revolution. So this is possible because of, you know, the foundations that these people and their team has laid down. So it is not just about the science, it's the technology and the way forward, you know, what we look forward to in decades, if not, you know, even centuries to come. So this is a very special prize because of these two reasons. And I would like to begin this talk by two disclaimers. You know, especially when you talk about violating Bell inequalities, it can lead to some, you know, thoughts on philosophy. Okay, philosophical ramifications, or, you know, debates on interpretations of quantum mechanics and so on and so forth. The purpose of my talk is not to discuss those aspects, because we have to realize that this prize has been given for experiments. Okay, all these three are phenomenal experimentalists, and the prize has been given for a series of experiments that they have done towards a certain end goal. So as an experimentalist myself, I would like to stick to the practical, pragmatic view and tell you about why these experiments are important, tell you why we needed all these experiments to enable this prize. You know, so I would keep it primarily an experimental talk. And of course, you know, the second disclaimer is when you talk about experiments, the devil is in the details, right? So there will be some details in my talk. So, you know, I will try to make it as, you know, accessible to this, you know, I mean, thanks a lot for turning up in such huge numbers. So I would try to make it accessible to as many of you as I can, but then I'm hoping that at the end of it, you will go back with at least some holistic understanding of what these experiments were about. Some of you will, of course, understand the details, but I will talk about some of the details to give the complete picture. So with that, we move on to, you know, talking about what these experiments were on. But I can see that, you know, there are a lot of you who are not from the field, let's say, of photons or even quantum physics for that matter. So I will spend a little time in the beginning telling you about some of the concepts that we really need to appreciate, at least to a certain extent, to be able to follow why these experiments were needed. So I will talk for the next few minutes on these concepts. So for some of you it's a reminder, but for some of you maybe it is necessary to follow the rest of the talk. Okay? So the first concept that I'll talk about is entanglement. Okay? So what is entanglement? And of course this could be a talk by itself, so I'll keep it brief, but just so that you follow the rest of the story to the extent possible. Yeah? So this brings me to this example, which actually is a very familiar example. So I'm hoping that many of you have actually already come across the Schrodinger cat picture. And if you watch Big Bang Theory, for instance, they made it into one of the episode highlights. So it's somewhere in our popular mindset also, the Schrodinger cat picture. So what happens in the Schrodinger cat picture? There is this cat, a cat which is inside a box. Of course, you can see the cat, but for the actual picture, the cat is in a black box. I have changed it so that you can see the cat for now. Okay? So there is a cat which is sitting inside a box and you can't see from outside this particular cat. Okay? This cat is not sitting alone. It actually has a vial of poison also sitting with it. Okay? So if the cat has the poison, then of course the inevitable happens, the cat dies. If it does not have the poison, the cat lives. But from outside the box, literally, we don't know what is the state of this cat. It could be dead, it could be alive, because we don't, of course we are discounting the fact that the cat could do meow or whatever. We are not going to get into that. It's a cat in a box which could be either dead or alive. Okay, and so that is the situation. So what do we need? We need some signal, we need some information to know whether this cat is alive or dead. For that we have this radioactive particle also inside the box. Okay, so if the cat does not have the poison, the radioactive particle does not come out of the box. But if the cat has the poison, the particle comes out, which is essentially this situation. You have a cat, it is of course alive, with the radioactive particle with it. This cat unfortunately is dead and the radioactive particle has come out of the box. So what this tells us is that the position or the state of the cat is actually linked with the state of this radioactive particle. So by knowing the state of the radioactive particle, or by either seeing it or not, right, we will know whether the cat is dead or alive. This is what entanglement is about. A pair of particles, let's say, which share a certain correlation, whereby if you measure the state of one, you know what is happening to the state of the other. So this is a way in motivating, the state of entanglement. Of course, this is how you can generate it and so on, but we will keep it to as little math as possible, but there are 4 slides with math, disclaimer, but we cannot avoid that, going forward. But then just to take this analogy forward, I see very young people here also. So the idea is that, if you like music, I'm sure you do, you may be listening to a piano, or you may be listening to the guitar or violin or something, and it's all beautiful. But if you listen to all of it together, then only you get this picture, this music which is some symphony that you actually wanted to hear in the orchestra. So entanglement is something like that. It is more than the sum of parts. It's not that, if you listen to this piece of music and then that and then that, then you get the whole picture. To listen to all of it together, which is essentially that an entangled state is not separable, which is of course, a very trivial statement, but what it means is as follows, that you cannot write an entangled state as a product of 2 states. So piano multiplied by violin multiplied by cello is not going to give you that symphony. Once it's entangled, it shares a correlation which is more than the sum of parts. Okay, and mathematically, for instance, this is how we write it. This is an entangled state. You cannot write it as a tensor product of the individual states. Okay, and of course examples of Bell states, these are our famous examples. These are the maximally entangled states or Bell states. So this state, you cannot write it as a product of something multiplied by something. So that is what is entanglement, right? And this is a picture of an entangled photon source from our lab actually. So here you have one of the photons, here you have the other photon. If this photon is H, then this guy is V. If this guy is V, that guy is H. But if you look at this thing, this intersection point, you actually don't know which cone your photon belongs to. If the first one is H, then you know the second is V. And if the first is V, the second is H. But a priori, this intersection point, you do not know which one it belongs to. And this is the point we actually focus on to get entanglement in the lab. So this is an example of actual entangled photons and how they come out when you take a picture on an intensified camera and so on. So this is entanglement, okay. Then we go on to, we go up a little bit in terms of the complexity of the things, but we keep it simple to the extent possible. We know that violation of what are called Bell inequalities actually signify violation of local realism. This is something you have heard, and I mean, you know, it's there in the abstract and so on and so forth. But then you have to understand what these terms mean. So what is locality? Okay. So there is this definition of locality, which is called Einstein's separability criteria, or special relativistic locality. Now this is a picture I'm sure all of you must remember from your undergrad days when you studied special relativity. This is of course a space-time diagram, and so if you have events which are within this cone, then they are called time-like separated. If you have one here and the other here, they are called space-like separated. And of course here you have the speed of light. So essentially this means that, you know, you have to be within each other's light cone to be able to pass some information from one to the other without violating the signaling condition. So this is what is Einstein's separability criteria, or special relativistic locality. Why I am stressing is this Bell's locality assumption is stronger than this, and we will discuss this as we go through the experiments. But this is of course a part of that, but there is something more to it than just this. But this you already knew. Okay. Then of course I go on to realism. So I start with some fundamental quantum questions, and this is where, you know, I would start asking questions, but then maybe not here because it's, you know, I'm probably going to speak for the whole hour. So, but these are questions you should be asking yourself, I believe. I ask them all the time. So, you know, when we deal with these principles of quantum mechanics, when we are working in the lab or otherwise, many things are quite counterintuitive. Even if I say that, you know, these are all mathematically explained and everything, they are not straightforward to, you know, just digest, right? So these non-classical features, as we call them, what do they reveal about the nature of physical reality, okay? How do we reconcile our everyday experience of this, what we call the macroscopic world, with the sort of weird behavior of the microphysical world described by quantum mechanics? And to what extent is it possible to test it in the macro limit? So these are all questions which I'm sure we ask ourselves sometime or the other. This brings us to the topic of realism. The classical realist worldview states that a system is in a definite state for which all its observable properties have definite values independent of measurement. Just as, I mean, you know, I like to take this example by picking one member from the audience, this case Tarun. You know, he's listening to me is the impression. If I look this way, he continues to listen to me is still the impression. So his state, you know, his act of listening to me, which is his property for now, is independent of my measurement, which is looking at him or looking at the screen. So this is what we all sort of, you know, want to believe, that tree outside is there even when I'm not looking at it. Somehow this appeals to us as what it should be right. However, unlike a classical state, the specification of a quantum state does not in general give the values of dynamical variables possessed by a system. In general, a dynamical variable is taken to have no definite measurement independent value. So till I look at him, I won't know whether he is listening to me or not. That is the analogy here. Essentially, in other words, a measurement according to quantum mechanics in general does not reveal a pre-existent value of a dynamical variable. So it has possibility of many values. Only by the act of measurement I'll reveal which value it wants to reveal at that time. That's the idea. So this is of course contrary to our, you know, everyday notion, I would say, and of course it did puzzle brilliant minds like Einstein himself when he famously says that, you know, he likes to think the moon is there even if he is not looking at it, which is what we would all like to think perhaps. But then in a quantum system, this breaks down, and so that of course lays the foundations for these experiments which show violation of local realism. So locality, realism, entanglement, these are the things we have covered so far, right? Next we go on to, of course, the main thing, which is Bell inequality, right? That is what we have to violate, of course. So let us do that. Let us not do that, let us understand what that is about. So here we have John Bell, okay, his picture, of course, and this is something at least the people in the second row, you know, the very young looking people, you should definitely read this because it's really very nice. It's a very nice article where Bell himself tells you about, you know, how, you know, he was also puzzled and how he came up with the inequality. It's a beautiful article. But then just quoting from that article, he says, you know, the philosopher in the street who has not suffered a course in quantum mechanics, suffered is a nice word, yeah, is quite unimpressed by Einstein-Podolsky-Rosen correlations. What is that? Of course, we'll come to that, but then the idea that there can be correlation shared by a pair of particles which are not co-located, which exist, even if you separate them, this is the kind of thing which puzzled, of course, EPR. So he can point to many examples of similar correlations in everyday life. The case of Bertelsmann's socks is often cited. Bertelsmann was a colleague and friend of John Bell, okay, and he was a very interesting fellow. He is an interesting fellow. He likes to wear socks of two different colors, okay. Which color he will have on a given foot on a given day is quite unpredictable. And but then this is John Bell's cartoon here. So when you see that the first sock is pink, you can already be sure that the second sock will not be pink, because of course they are different colors. So observation of the first and experience of Bertelsmann that he won't wear matched socks gives immediate information about the second. There is no accounting for tastes, of course, pink, non-pink socks, it's his personal taste, but apart from that there is no mystery here. And is not the EPR business just the same? So he poses this himself, the correlations, so what is so special? Something is this, then the other is this, I already know, even his socks are like that. Of course it is not like that, because this is a correlation that is beyond just this is a very classical correlation, so it's completely different from that. But then Bell himself asks this question and goes on to of course answer it, and this is, by the way, Reinhold Bertelsmann showing his socks in Vienna, okay. You can see it's pink and yellow, right? So in fact he sticks to that even till date, right? So the best known set of experiments which examine this question of realism are of course these EPR Bell experiments. As we said, they refer to measurements made on a pair of systems which have interacted in the past but are now separated to a distance, such that according to the postulates of special relativity, outcome of a measurement as one system cannot be causally influenced by the choice of what to measure on the other. This is what it is, and of course we'll understand this in detail. So this is what happens, of course, in the EPR Bell scenario. You have a source of correlated particles, mostly photons in this case, and so one of them goes to the Alice station, one of them goes to the Bob station. You perform some correlated measurements, and we'll get to what those measurements are, and you violate what is called Bell inequality. So we will now understand a Bell inequality. These are the details, but we'll skip it for now because we'll anyway study it. But this is a very important observation from Bertelsmann as well, that when he saw this inequality and the fact that this is all possible, he was very, very amazed that John Bell could come up with these. How did he know how to construct these inequalities? It actually was something that was puzzling to him, and for him as a theorist the job was done. Nevertheless, the experiment had to decide which was right, and so that is what sets the basis for our prize this year, which is this series of experiments, right? Which brings me, I have marked the slides that there is a little bit of math in the next 3 slides, but it's quite straightforward in some sense. I want to show you how to derive a certain form of Bell inequality, okay? So here I have Alice, I have Bob, 2 famous characters. We have made them famous by calling them again and again Alice and Bob, so let's say A and B. Alice chooses to perform one of 2 possible measurements, A0 or A1. Okay, these are binary measurements. Bob also does the same thing, chooses between 2 binary measurements, B0 or B1. Okay, so binary means one or the other. So result of A0 is +1 or -1, likewise A1. If you make 2 assumptions, what are these 2 assumptions? Each measurement revealed a property that the particle already possessed, independent of being observed or measured. And if you recall, that is realism. That's the first assumption that we need to derive this inequality. Second is Alice's choice of action cannot influence Bob's result or vice versa, which of course is locality. Making these 2 assumptions, we can actually see how the inequalities come through. Example, Alice chooses to measure A0 and obtains the result +1. How can she do that? Because it was pre-existing. So she already has obtained this result +1. Then the particle she received carried the value of +1 for a property A0, right? Now you choose this following combination, okay? A0 B0 plus A0 B1 plus etc. And you can just rearrange the terms. Then of course either A0 equal to A1 or A0 equal to -A1, because it's either plus or -1. So trivially either one of them will be 0 in either of these conditions. So the other term will then evaluate to ±2, because that's what the properties are. So you repeat it over many trials with new pairs of particles, average over many trials for the combination, this combination, it will obviously be less than equal to 2, right, because each of them has a maximum value of 2. So no single trial can measure the quantity because Alice and Bob choose one measurement each at a time. But on the assumption that underlying properties exist, average of sum will be equal to the sum of averages. That's of course very important because that is what makes you write this. So this is the sum of average over these measurements that you have done, which we showed in the previous slide. That is then less than equal to 2, right? This is what is called the CH-SH form of the Bell inequality. Clauser, Horn, Shimone and Holt, these are the people who came up. So there are many forms of Bell inequality. So Bell himself had a certain form, but that was not so easy to do experiments with. In fact, this is the one which is the most standard one right now, because it's amenable to testing experimentally. Okay, this is one popular form. What happens in quantum mechanics? Now, if you consider this Bell state, we just saw this earlier. Alice's measurements are, these two Pauli measurements. Bob will choose these two. So this choice of measurements actually maximizes the violation. But then you can have other choices which may not maximize, but then the maximum is the case I want to discuss. So if you now, you have to do the math, I'm not going to show it, you measure the quantum expectation values using Born's rule, it will actually come out to this. For this state, if you do the, bracket algebra, each of them will be 1 by root 2. And of course this one will be minus. So this then becomes 2 root 2. The thing that we saw was 2 for the non-quantum case, let's say, becomes 2 root 2. So anything between 2 and 2 root 2 violates local realism, and quantum mechanics is a theory which actually agrees with this. It's not the only one, but then of course we need to see what the experiments tell us, whether they agree with quantum mechanics or not. But for now we definitely know that quantum mechanics definitely predicts a violation of the Bell inequality. Okay, so that was the math part done, and in fact there is no more math in the rest of the talk. Okay, but then this was necessary a little bit to give you a feel for how this all came about. Now I go on to talk about what I really like to talk about, which is of course the experiments that actually led to this Nobel Prize, right? This is the first experiment. This is John Clauser, this is Stuart Friedman, okay, and they performed the first experiment which violated Bell inequality. Now there's a very nice story behind how this experiment happened, and it's quite instructive for the students. So you have John Clauser, he's actually done his PhD in astrophysics. And so he lines up to do a postdoc in University of California, Berkeley, and he gets very interested in foundations of quantum mechanics at that time. So he turns up to do this postdoc with Charles Townes, who is a radio astronomer. So this is, a radio astronomy community at RRI should be very thrilled with this prize as well, because it's actually a person who did part radio astronomy, who did the first experiment to violate Bell inequality. So he, however, was very keen to do this experiment. He came there because he knew there was a setup already, which was, done by Cummins and his PhD student. And this was to produce these pairs of photons. So he wanted to use that and perform the Bell test. But then nobody wanted to sort of give him time for that, because you're hired to do astro, you better do astro. But then RRI knows better, and so then this guy he was able to convince his supervisor that I really want to do something with this setup. So then he was convinced, the supervisor, and he spoke to Cummins and said that I want Clauser to spend half his time doing this experiment and the other half doing radio astronomy. Okay, and so then Cummins said that no, then my PhD student also has to be involved. So Friedman came in, who was a PhD student of Cummins. So then that led to this collaboration between Friedman and Clauser, where Clauser worked on this experiment for half of his time and was able to do the first violation of Bell inequality. There's a collaboration between radio astronomy and quantum. It's RRI, as some people know, is one of the leading places for radio astronomy research and astrophysics in general. So it's I'm sure some of my colleagues are pleased with the story. So this is how this went. Of course, there are assumptions. The first experiment. So there are of course many assumptions which get broken as we go along. It's a story. Of course, it's Vignyana Kathegalu, so it has to be a story, but this is, this is how it builds actually. So they are separated localized particles, the binary selection happens, either transmission or no transmission. That is the kind of assumption. All photons incident on a detector have a probability of detection that is independent of whether or not the photon has passed through the polarizer. We will see later that these assumptions are not quite great and how they get changed and so on. This was the, this calcium, this is the calcium atom, and so this was what they used. So, resonant absorption here, this 7% chance of going to this state, and then through a cascade effect, it comes down to the ground state, and these are the two photons which get generated, which are correlated. Okay, so this was their system, and of course they had these polarizers on both sides, PMTs, photomultiplier tubes to do the measurement, and coincidence measurements is what they did. Okay. What were the experimental ingenuities and what were the conclusions of this experiment? This is the main thing that they did really. This requirement for large, efficient, linear polarizers. That is what the previous experiment did not have. That's why the previous experiment did not show any Bell violation. But this is what they did. They did this pile of plates polarizers. They used this for the first time. Many polarizers stacked together to kind of increase the efficiency. So this was one of their main contributions. This is the inequality they violate. I told you there are many forms. This was their form. Lot of cycling, averaging procedure, and 200 hours of data. And so this is, this R phi by R0 as a function of phi. So all error limits are 1 standard deviation. These are the two values, and again I told you that's why these two values have a significance. They lead to the maximum violation here as well. So they got 0.050 plus minus 0.008, which of course is a clear violation of the above inequality. You have to get 0 for this. So it's clearly non-zero. Okay. So no evidence of a deviation from predictions of quantum mechanics either, calculated from the measured polarizer efficiency solid angles. So strong evidence against local hidden variable theories. This is the first experiment and it already showed a strong evidence. Okay. Enter Alan Aspect, the second Nobel laureate this year, and of course it's not just one experiment. This is where Alan Aspect actually did a series of experiments where he went on to improve on his previous versions. And I take a pause here to just make a very general point here. This is the kind of thing which, motivates you to, I'm hoping some decision makers should also listen to this, that, you don't always get results in a year or 2 years. You need concerted effort to go towards that, whatever final goal you have set yourself to. So you need to have these, breakthroughs one after the other to reach a final goal, and of course funding is very essential for that. So this is actually, this year's Nobel Prize is a case for that, although they are not from the same group obviously, but it's a community which actually has helped in improving on previous results over decades. Okay. Another example would be LIGO. The LIGO Nobel Prize, of course, again, decades of effort, but by many people putting in different pieces. This is different, but in some level makes a case that, you cannot necessarily do the ultimate thing in 6 months or something. You can't always do that. So you have to take steps, and that is the story behind this year's prize, right? So this is the step. So what did these guys do? This is Philippe Grandier. I did not find a picture of Gerard Roger, unfortunately, on the internet, but these are the 3 people. Okay. So this was again the same, calcium atom, but the change here is that instead of resonant absorption, they actually, they selectively pumped to the upper level, and then there was this decay to the ground state. So instead of resonant absorption, they did selective pumping. So they used it slightly differently. This was their setup, but then again, what were their contributions really? The inequality remains the same. This is your experimental result. So this is the violation, and of course it's more than 13 standard deviations and in perfect agreement with quantum mechanics again. Okay, this is their graph. So another thing they did, they moved each polarizer 6.5 meters away from the source. That is, it's 4 coherent lengths of the wave packet associated with the lifetime of the intermediate state of the cascade. So no change in results was observed. This is another important point. Of course, the results in excellent agreement with quantum mechanics and strong evidence of violation of local realist theories. This was another new element that they added. No effect of distance between measurements on the correlations was observed. This is the first Aspect experiment. Okay. The second Aspect experiment along with same collaborators. So now you would say, what was the need for doing so many experiments? We have been violating Bell inequality, we are disproving local realism, all that. So why are they doing all these experiments? of course, that is what brings us to the important point, that these experiments, they leave certain loopholes. What is a loophole? A loophole is some sort of a, in a loophole in an argument, when we say we are fighting a case or something, there is a loophole in that argument. This is another way of explaining this. That is a loophole even in these tests, right? So it is possible that, these results, they are violating Bell. Let me give you an example. The one that is easy to motivate is what is called the detection efficiency loophole. There is an assumption there, and I already showed you that in the first experiment, that the detector, of course it is detecting the photons, but it is not detecting everything, because the detector does not detect everything that is incident on it. It has limitations because of its efficiency. Now there are certain ensemble of photons which don't get detected, and there is an ensemble which gets detected. But the ones which get detected, they have shown Bell inequality violation. Very nice. What about those which didn't get detected? Suppose they actually end up agreeing with Bell inequality. It's a possibility. It's a loophole. So if we don't have an answer to what those photons did because they never detected them. That's an example. There are, of course, many things. So that these are the kind of assumptions which need to be closed, so that there is no other explanation than the explanation that is being given again and again. That is what it means to close loopholes. Okay, and so this is, so why did they do this experiment? Now this is the EPR setup, right? You have a source of correlated, let's say, photons, of course, in this case. So these are, being sent to the Alice station, Bob station, and then there are two spin components on each side that can be measured. This is important. So this then leads to this sort of a probability, expression, and this is called the Bell parameter. So you have, 4 of such possibilities, because there are 4 on each side. So each of them is dichotomic. So this is what EPR actually, wanted in their Gedanken experiment. So experiments till then, including Aspey's own, did not follow the scheme of figure 1, okay, closely enough. Some experiments were performed, with this cascade of, this calcium and so on, but true polarizers were available in the visible range, but all of the previous experiments involved single channel analyzers, which means that you transmit one polarization, block the orthogonal. So it's only one that you can do. You cannot do all. So essentially, they could only measure this guy, but not the other 4 in the same. They would do many experiments and pull it together, but not in the same run. So this was one of the issues. So why was it an issue? Because you see, these detectors were very inefficient. They were photomultiplier tubes. So measurement of polarization is inherently incomplete. This is very important. If no count is obtained at the PMT, it could be because of low detector efficiency or because it has been blocked by a polarizer. Now this is the case we want, this real polarizer measurement. But how do you distinguish? Because the only thing you allow is either it goes through or doesn't go through, right? So these cannot be measured directly in these previous experiments. Auxiliary measurements were required. Then you have some form, but not the exact form. So what were the ingenuities in this experiment? This experiment follows much more closely the EPR Gedanken experiment. True dichotomic polarization measurements on visible photons were performed. So replace these polarizers by 2-channel polarizers. So separating the 2 orthogonal linear polarizations. And for people from the lab group, you know that this is essentially polarizing beam splitter, which was not used earlier. So you can then separate, then you have 2 PMTs on each side, not just 1 and 1 like it was earlier. So each polarizer is mounted on a rotatable mechanism holding 2 PMTs, and this ensemble is called a polarimeter. This makes it very similar to the usual Stern-Gerlach measurements for spin half particles, which was the original intention. So this is now a picture which is slightly changed from the previous ones. Here we have this ability to distinguish between orthogonal polarizers. So now you have PMT here, another here, and you are doing this. What it leads to is a 4-fold coincidence, so all 4 together, right? And the 4 coincidence rates are measured in a single run. This is the big advance over the previous one, where you had to do them separately, then there are assumptions and loopholes. So this is what they did. This was their quantity, repeat, so on and so forth. Important. Again, by now you are familiar with this. You have the experimental result, you have the quantum mechanical, and of course they are matching. Yeah. So very nice match. Graphs also match, so on. So strongest violation of Bell's inequality is achieved till then, an excellent agreement with quantum mechanics. Straightforward transpositions of the ideal EPR scheme. Procedure is simple, simpler than it can be otherwise, and needs no auxiliary measurements like the previous experiments. But then why do we have the next experiment? There must be a caveat. This is how it is, right? So this is end of episode 2. But why do we need episode 3 in our novel? Because something is not quite settled yet. What is the caveat? The assumption that the ensemble of actually detected pairs is a faithful sample of all emitted pairs, that is called this detection efficiency loophole or the fair sampling loophole, which we just discussed. They have taken care, to have different conditions, ensure conditions that are similar in different runs of the experiment, but it still remains a loophole. Thus, two main loopholes remain: the above detection efficiency or fair sampling loophole, and then the static character of all previous experiments. So what is the static character is what we will come to next, which actually is called the freedom of choice loophole. So if you have these polarizers, you're fixing them, you're doing the measurement, fixing them, doing the measurement. That is what has happened so far. So there is a choice involved. So it seems like you have this freedom to fix it. That freedom also should not be there. And that is what leads to the third, the second aspect, of course, contribution, and the third overall, which is using time varying analyzers. There is no static character now. Okay, and this is of course a phenomenal contribution. This was John Dalibard, by the way. Again, Roger picture I don't have. Bell's, now this is very important. I told you that we talked about special relativistic locality. What is Bell's locality? What is the additional thing we need to understand about Bell's locality condition, strong locality, and why experiments so far are inadequate, right? All experiments so far have been performed with static setups in which polarizers are held fixed for the whole duration of time. Then you change it, again duration of time. One may then question Bell's locality assumption that states that the results of the measurement of polarizer 2 does not depend on the orientation of polarizer 1, nor does the way in which the pairs are emitted depends on A or B. Okay, so it is basically once you have set it, then the photons are going, you're doing the measurement. But then there is nothing changing while these photons are in the flight, so to speak. So there is, there you can come up with a loophole. And this may be reasonable, but there is no fundamental law which prescribes this. In fact, Bell himself points out. He says that the settings of the instruments are made sufficiently in advance to allow them to reach some mutual rapport by exchange of signals with velocity less than or equal to the speed of light. What does that mean? So before you do the actual experiment, we are doing the experiment, we have decided on some kind of a map. If you do this, this will happen. If you do some map, you can decide. And then, when you're doing the experiment, you can follow that map. So this brings about a problem. You should not be allowed to do that. This Bell himself points out, of course. And if such interactions exist, then Bell's locality condition would no longer hold for static experiments, nor would Bell's inequalities. Bell thus insisted on the importance of experiments in which settings are changed during the flight of the particles. And this current aspect paper reports the results of the first experiment using variable polarizers. This is the major achievement of this experiment. Okay, so what are the ingenuities? So now this is the picture, but this is what you need to see. There is a switch here. They introduced this concept of an optical switch, and in fact this is the very nice theory paper where he proposed how to do this and then did the experiment himself with his colleagues. So this is what is called an acousto-optic modulator. So the switching of light is effected by acousto-optical interaction with an ultrasonic standing wave in water. So essentially this beam goes, either it gets transmitted or deflected. So this is being done by an AOM, as we call it, and this switching is what gives it the dynamic character which was missing in the previous experiments. Okay, and of course another important point here, see these channels, this switching occurs each is about 10 nanosecond after because I think we have a 1 hour and then is that how we would do this then? Yeah, because otherwise people will leave. So you please note it, Sumati. Yeah. So this switching is occurring, so I was saying that it's 10 nanosecond. 10 nanosecond is very important. Why is 10 nanosecond important? Because 10 nanosecond and the lifetime of this intermediate level is 5, and it is small compared to L by C. So L by C is this 6 meter. So I have that. So 6 meter. Each switch is 6 meters from the source. So if you take that 12 distance divide by speed of light, you will get a number which will be actually this. Okay, so essentially a detection event on one side and the corresponding change of orientation on the other side are separated by a space-like interval. So this is very important. Okay, and again we have the violation. Okay, so what next? So we have actually solved one loophole. I mean, not we, Alan Aspe with his genius contribution, he came up with this variable character. The new feature of this experiment is that the settings of the polarizers are changed at a rate greater than C by L. However, the ideal scheme is not completed, okay? And the change is not truly random, but rather quasi-periodic, because ultimately still it is going from one to the other, and that it's not because of some random number generator that you have used. That is missing so far, okay? The switches on the two sides are driven by different generators at different frequencies. Thus it's natural to assume that they function in some uncorrelated way, but a more ideal experiment with random and complete switching would be necessary for a fully conclusive argument, okay? And the next work actually reports this ideal experiment. So that's the story, right? So this is how this proceeded. So now we have an ideal experiment which actually does this. Again by, now the third Nobel laureate for this year, Anton Zeilinger, along with his students and postdocs at the time, Gregor Weiss, Thomas Genevine, Harold Weinfutter, and Christoph Simon. So I have highlighted what is necessary here in the abstract. The necessary space-like separation of the observations is achieved by sufficient physical distance between the measurement stations, by ultra-fast and random setting of the analyzers, and by completely independent data registration. Another two important contributions from this particular paper. And I digress a little bit to say that, Gregor Weiss and Thomas Genevine were my postdoc mentors, and so I'm a little bit like an academic granddaughter of one of the Nobel Prize winners, which makes me feel very happy for a change. And so they were there for the opening of my lab. These are them cutting the ribbons, and also it's actually very, very thrilling that they have contributed to this year's Nobel Prize winning work, and of course we know them so well. So this is Gregor and Thomas. So going back to what is needed. What did they do? What is needed to close the locality loophole once and for all? This is from their paper. Aspe et al., however, used periodic sinusoidal switching, which is predictable into the future. Thus, communication slower than the speed of light or even at the speed of light could in principle explain the results obtained. And they have actually written a nice paper on this. Therefore, the second loophole, which is this locality loophole, remains open. Okay? So the individual measurement processes of the two observers should be space-like separated. This paper, the Zeilinger paper, defines an individual measurement to last from the first point in time, which can influence the choice of the analyzer setting until the final registration of the photon. They actually do that. This is an important one as well, but this is what, of course, is the main contribution. The individual measurement was so quick that it is impossible for any information about it to travel via any channel to the other observer before he in turn finishes his measurement. And so this is what led to this, and it has to be completely unpredictable. You need a physical random number generator. Pseudo random number generator cannot be used since its state at any time is predetermined. Okay? So to achieve complete independence of both observers, one should avoid any common context also. And this is the second important point, as would be, so what do? We conventionally register these coincidences in all the previous experiments. Here what they have done, the individual events, they are registered on both sides independently and compared only after the measurements are finished. So Prabhakaran, Sujata, these people will know what we are talking about, because this is what we now use all the time, but this is the first time this happened, that they compared it later. This requires independent and highly accurate time basis on both sides. This is their space-time diagram. So this is, of course, again, the same thing. What were their ingenuities and what is the conclusion? For the first time, any mutual influence between the two observations is excluded with the realm of Einstein locality. The two observers are separated by 400 meters across the Innsbruck University campus. Individual measurements are defined to be shorter than 1.3 microsecond. This is the time for direct communication at the speed of light. And theirs was far below 1.3 microsecond limit, using high-speed physical random number generators and fast electro-optic modulators. Okay. Now, so this is a different kind, not acoustoptic, electro-optic, and you should remember this for the last part of my talk, where this will come up again in modern settings. So this is the first time these things were used in Bell inequality. Independent data registration, as I mentioned, was performed by each observer having his own time interval analyzer and an atomic clock synchronized only once before the experiment cycle. Source of photons was type 2 SPDC, which is what people like us are using now, and silicon APDs were used, not PMT. Avalanche photodiode detectors come in because they have much lower dark count, which means much lower noise, and so much smaller than the signal per detector. So lots of advancements in this particular experiment. This is the picture, and these are for the 4 settings, their curves as a function of the Alice settings. Okay, and so this corresponds to a violation of the CHS's inequality of 30 standard deviations, assuming only statistical errors. Okay, so this was their contribution. So which major loopholes remain to be closed? So we have dealt with many. We have now also done the foolproof locality loophole closure, fair sampling loophole, of course. You know, the detection efficiency still remains an issue. So what did Bell say about this? Bell says that, you know, it is hard for Bell to believe that quantum mechanics works so nicely for inefficient practical setups and is yet going to fail badly when sufficient refinements are made. We'll have very good detectors and it will fail. He found it a little difficult, which is true. Of more importance in his opinion is the complete absence of the vital time factor in existing experiments. Analyzers are not rotated during the flight of the particles, and this is what the current Zeilinger experiment, you know, closes, the timing or locality loophole. However, still it's not loophole free yet, right? That is where we want to go, and this is of course Zeilinger's contribution along with several other people. I stopped putting pictures at this slide, you know, but then so this again you can see here. So this is a significant loophole free test of Bell's theorem with entangled photons. They report a Bell test that closes the most significant of these loopholes simultaneously. Okay, so they have used a very nice source, they have used highly efficient superconducting detectors, and they observe a Bell inequality violation with high statistical significance, and of course importantly locality and detection loophole have been closed simultaneously in this experiment. So this is of course the loophole free experiment which really you know got Zeilinger, I mean, you know, and there were two more which happened with other systems, but then we are sticking to the Nobel Prize in Physics 2022. So this is the timeline. So this is when EPR came up with their argument. John Bell comes up in 1964 with the Bell inequality, and in 2017, 15 to 17, we have the loophole-free experiment. Okay, so and 2022 we have the Nobel Prize. So this is the number of decades it took to reach a loophole-free violation of Bell. So why is a loophole-free test so important? Okay, now, of course it is important because, you know, as I told you earlier, what are loopholes? They are alternative explanations. So if you're trying to say something that yes, strongly you have done something, you don't want an alternative explanation. So naturally now we have no doubts that we have violated Bell inequality and local realism. Well and good, but that's not it. It's also about these applications. It is these violations which have led to these applications, including perfectly secure quantum key distribution and unhackable sources of truly random numbers. This is of course equally important point. Why we need a loophole-free test, and this is a very nice article if young people want to read this. Okay, and it gives me great pleasure to say that we have done a similar experiment earlier this year, where we have done a loophole-free interferometric test of macro realism using heralded single photons. So this is what is called the Leggett-Garg inequality. So we have been talking about Bell inequality so far. Leggett-Garg inequality is the time equivalent of Bell. Several decades people have been working on Leggett-Garg as well, and so it is actually indeed a proud moment for us that we have been able to do a loophole-free violation of this in early 2022, the same year that loophole-free violation of the Bell inequality has received so much attention and honor. So it's and Komudi here, also got us some Bell violations to show you, just, to give you a bit of context that all this is not old hat. This is actually being done actively in labs like ours. So this is of course for maximum violation you need this. It's an ongoing work, I won't discuss the details, but we actually, use this state for a reason which we won't get into. Estimated violation is this, but then you can see that we also violate the boundary for obtaining local realism, and there is more to it which I will skip for now. So just to give you a little context, okay. Coming back to the last part, which is about the technology. So this is what of course makes all this a nice story, because otherwise it's just a story. Different people have come and closed loopholes, and finally we have a loophole-free test. But then what do we gain from it, right? That is what I want to answer in the next 10 or so minutes. This is from the Royal Swedish Academy of Sciences, so they have a nice write-up on this year's prize. Do have a look at that. And so this is beautiful to me, so I just want to share it with you. Bell's inequalities are not just a matter of quantum mechanical ontology, okay, but can be put to practical use. So, you have Clauser's experiment, they go through the loophole-free version, and Zeilinger managed to simultaneously close both. We have gone through this story. The main importance of these results is not to once again confirm that quantum mechanics is correct, that we are doing fine, but rather to enable even more secure QKD protocols. quantum key distribution. Since these depend on Bell tests, the issue here is not whether nature conspires to violate Bell inequalities. That is where it gets the philosophical thing. But practically, whether the evil eavesdropper does. We are worried about the eavesdropper now. We don't really worry about nature per se, but what does an eavesdropper do? In 2022, 3 groups used Loophole-Free Bell tests to experimentally realize device-independent quantum key distribution protocols. A fantastic achievement. I mean, it's these are great experiments, you should read them. This means that the key is secure even if Eve has access to quantum hardware that runs the distribution. For details you can look at the papers, but this is what is important. So this prize is not just about closing loopholes and sitting pretty. It's about using them in what we are doing now, what we'll continue doing for years, decades to come, right? So before we go on to understanding, so if anybody is paying real attention, I told you to keep track of 2 things. Do you remember what those 2 things were? I highlighted them and said they'll come later. Maybe not. It's too much to. Somebody is actually volunteering an answer. Excellent. Switching and physical random number generator. Good. You are listening. Good. I'm so pleased. So, this has enabled secure quantum communications. If you remember this fast switching on EON in the Zeilinger experiment, now it is used in quantum key distribution all the time. So these are all experiments where they are using it as if, it's just commonplace, but that was the first time. So this is what it has enabled, right? This switching is a great example. But of course, what we are looking at right now because of this prize and what it has enabled is this, which is a global quantum communication network, right? Here you have a secure quantum network which is connecting the entire globe through fibers, through free space. All this forms a part of this year's prize. And in fact, we will see that Zeilinger's contribution is not finished with the Loophole-Free. That is still remaining. And this is a slide which, is important because it tells you what kind of distances you can achieve with which technology. And they're all using entanglement and Bell inequality violation. So this is where we are looking at, right? And then comes again, of course, Zeilinger's contribution, as I said, is not over. He is the first one, along with his colleagues, to demonstrate experimental quantum teleportation. And that is also a part of his prize, okay? And so, of course, Dirk Baumister and Junwei Pan, who again has done phenomenal work, of course, as we all know. And this is the first quantum teleportation experiment. This is, of course, Charles Bennett's original paper on teleportation. I won't go through the details here, but essentially quantum teleportation is a protocol which uses entanglement as a resource to be able to send an unknown quantum state from one physical entity to another by using entanglement as a resource. It's a quantum information transfer protocol. It's not a key distribution protocol. It need not be. It's also quantum communication, but state transfer is what it does. We won't do the math here for a change. And so these are the recent ones. So this is a free space quantum teleportation, which is a 16 kilometer, and then we have 143 kilometer. So these are all results from yesterday and today. And there will be many more from tomorrow. And that is what we are excited by, right? This is ground to satellite quantum teleportation. This is chip to chip quantum teleportation. So people are working in different architectures, chip based, ground to satellite, fiber. There's nothing left, it's very vibrant right now. And so this is, of course, what Zeilinger also contributed, the first ever experiment on quantum teleportation. And I have smiling students there who are working on our own version of quantum teleportation. So this also is his contribution. Entanglement swapping, I'll tell you what that is. That is his second, I would say, contribution which is in the technological domain. But again, using entanglement as a resource. Zeilinger and Junwei Pan, again, I have chosen to show their pictures. What is entanglement swapping? So here you have something which, some of us did, people here maybe 10 years ago, but then for the rest of us, some decades ago, we used to play the relay race. There used to be this baton, so we would run. I mean, I was not very good at it, but we would run to the opposite team, give the baton to one of the people there, would then come and hand it over to the second guy here, and this is what we call, the baton gets transferred from one to the other. That's the relay idea. So what we want to do is transfer the entanglement from one pair of particles to the other. That is called quantum relay, okay? And so what that means is that 1 and 2 are entangled, 3 and 4 are entangled, but I want to entangle 1 and 4. How do I do that? I do what is called a Bell state measurement, Okay, we won't get into the details of that, but if I do that, 1 and 4 become entangled. So I've swapped the entanglement from being between 1, 2 and 3 and 4 to being between 1 and 4. This way you can have entanglement distribution over long distances. But beyond a certain point, you can't keep doing this. You need to store that information at some point also, because you need to be able to, do the swapping also at will at some extent. So there you need what is called a quantum memory. So when you have a quantum memory, you store the state and then you release it to the photon when the time is right. And so together with memory and relay, you have a quantum repeater, which is one way of doing a global quantum communication network. And so these are, highly efficient entanglement swappings experiments that I have. This is 2022, and these are all things which are very buzzing, lot to do actually in the next several years. And this is, as I said, state of the art in quantum memories. This is what people have been able to achieve via fibers over dozens of kilometers. Here we have atomic ensembles separated by some 12.5 kilometers telecom fiber. So this is how people are progressing in this field by using, of course, entanglement based experiments and Bell state measurements, right? Then we just talked about device independent quantum key distribution. This cannot happen without entanglement. So you can do quantum key distribution with and without entanglement, but you cannot do device independent quantum key distribution without entanglement. That is why entanglement based QKD has a certain special notion. And so these are results from this year, and all of them are phenomenal. So they have been able to show device independent QKD in different platforms. The other thing that is very, very interesting right now is device independent random number generation. So this was the first paper which, again, using Bell's theorem, right? So if you violate Bell's inequality, you can generate random numbers which are much more random than the other possible ways of generating random numbers. This is the theory paper. This is the first experiment which showed this, okay? Experimentally generated randomness by violating Bell inequality. So you see how Bell inequality is coming in, entanglement is coming in as a commonplace thing in our conversation right now. And then this is another recent result, okay? Satellite-based secure quantum communications. This is the other thing that this has enabled. As I mentioned, long-distance communication, you can do it using repeaters, but you can also do this using satellites. This is the general idea. You have an entangled photon source in the satellite. One goes to one ground station, the other goes to a second ground station, and by doing some operations, you can link up these two. That has already been shown by the Chinese satellite Mishias. So these are all their results, okay? But then there is a lot left to be done. And in fact, again, we're very happy to say that I can take a state-of-the-art example through our own ongoing project on satellite-based quantum communication, which is quantum experiments using satellite technology. And it's a collaboration with ISRO. It's the first project that we have started as a country. We're very excited at being able to do this, right? And so we are going to demonstrate this quantum communication using entanglement between two ground stations using a satellite as a trusted node. But we are not going to do the downlink. We're actually planning to send the photons up. And there are reasons to do that which make it more exciting, I would say, than the downlink options. So we've achieved many milestones, and we're very excited going forward, right? Just to give you an example of the second point that you raised, right? So you remember 2 points, I'm very pleased with you, but then the second point was this physical random number generator. Now, just to take an example from our own lab, we did this experiment where we were able to get these competitive key rates and QBER because of certain ingenuities. One of them is this physical random number generator. People were using pseudo-random number generator in earlier experiments. We used the same idea as that Zeilinger experiment, which of course was the first one which did that. So, it's all being used in a commonplace way now, and a lot to look forward to. So this is essentially the last slide of my talk, where I want to say that, this year's prize is in fact very well summarized by this quote, which of course is said in a different context. We won't talk about the context here, but then indeed this is what it is, that, the science that these three stalwarts enabled along with their group, the huge groups of people that they worked with, has enabled today's and tomorrow's technology. And in fact, Zeilinger, of course, is participating very actively in many of these technologies, and his prize is also about some of the technology that it has led to. So I hope I'm on time, so thank you for your attention. Yeah.
Thanks, Urvashi, for the wonderful talk. So I'm sure there are lots of questions.
I thought, Sanjukta, you were going to ask a question, so thank you very much. Yeah. Yes, Shantan. Yeah.
Great talk.
Thank you.
So, so I was wondering that you spoke about this efficiency of the detector. Initially, they were not very efficient. Now,
Right.
this Zeilinger, he used superconducting detector. So now that we know that we have very high efficiency detector, so now can we say that whether the detector efficiency matters at all?
Yes, that's an excellent question. So, you know, if you actually, so you can, so I skipped those sort of details here, but I want to answer your question in the proper way, that you can actually do very full-blown calculations using these, different kinds of models for Bell inequalities and other inequalities, where you can come up with the critical detection efficiency that is required to call it free from detection efficiency. So for these experiments, for the CHSH Bell, it's actually around 66, 67%. Okay, so that is the bound. So beyond that, you can say that detection efficiency loophole does not matter. That is, so you can do these calculations. But for the Zeilinger experiment, it wasn't just about using these SNS, those have greater than 90% efficiency for sure. But they actually used a different form of the Bell inequality, which is called the Eberhard form of the Bell inequality, where actually you can derive the inequality without assuming a perfect detector. So that was another important point in their experiment. So they not only used excellent detectors, but they also did this using inequalities where this is not an assumption. Yeah.
Thanks.
Yes, Sumati. Sorry, I didn't take your question earlier.
Yeah, that question I think you answered
Okay.
in the talk. So I just wanted to, with all of these quantum communication things, one, because of the, the time scales that one is talking about, etc., I've never quite understood how decoherence can be dealt with, because, doing something in a lab where the time scales are very short and showing it is one thing, but once you interact, so to speak, with the classical world,
Yeah.
just as measurement does that for you, typically,
Yeah.
the issue of how do you retain coherence over such long periods of time has always been a mystery to me. So
Yeah.
if you could shed some
No,
light.
that's actually, again, a very nice question. So, see, the point is that what the question that you ask is, in fact, a part of what we do, one of the subparts of not just we, the community that is working on. That is one of the calculations, again, it's a calculation that is done, where we take into account, for instance, if we talk about free space, that is what perhaps gives us the biggest distance. Fiber, you cannot go beyond a certain distance because you need a repeater. And so you violate no cloning. So you can't do that. So if you want to do free space and use, for instance, a satellite, which is where you talk about this 600 kilometers or whatever. So we actually take into account the static and dynamic properties of the atmosphere and calculate what will be its effect on the property that we are using for the key distribution. So now there are papers which say that polarization is more robust as a property than, let's say, some of the others in a long haul experiment. But then there are parallel experiments which people are doing where they are using time bin as a property. So these are all ongoing efforts, both experimental and very theoretical ones, to come up with an answer as to how much we expect to actually preserve. But there is more to it. So you won't preserve everything. And in fact, this is closely related to something we've very recently done. So it's something I can answer very well. We actually, and so Anindo is leaving because he has a talk. It's not because he doesn't like mine. Okay, so yeah. So, but then coming back to your point, so we actually, did an experiment where we tried to see how much of the entanglement we preserve when we go to a longer distance than within the lab, So the people, what they do the entanglement characterization and then they do the protocol. They don't in situ measure entanglement anymore. But we actually realized that, in spite of all best efforts, there is some loss. There is some scrambling that is brought about by various sources. Birefringence is one of them and many others. So what you need then is a feedback mechanism. Okay, so there are two types of feedback mechanism. One is what is called an active feedback mechanism, where what is happening is that you actually have a separate channel where you are sending a light just to measure the scrambling. Okay, so maybe a strong light, even not your photon beam, but strong light. You are using that to come up with, how to correct for the state. Because as you very well know, the Bell inequality, if you want to violate it, the settings very much depend on the state. So if I don't have that same state, then of course it's not going to work. And that is that ongoing work that I alluded to. We're understanding something better there. But then having said that, this active feedback mechanism is used to actually correct for this polarization, and we have what are called polarization rotators, okay, or bat ears as they are called. So they use birefringence again to actually, they have wave plate combinations which are used to correct for this loss because of the feedback that I am getting. That is one way, okay. So if you can, you're thinking. So feedback is very important, and so
it sounds more classical.
this part is, as I said, the feedback is actually received by using a classical signal. Yeah, so this is a correction that I need to do to ensure that the settings that I am using for whatever experiment, Bell or whatever, remain true to the state that I actually am assuming. So this is done, and this is done. Many interesting things have happened. They have used robotic arms and lots of experiments on this. But what we have done very recently is, this active feedback actually involves more resources. Okay, so we have come up with a passive feedback mechanism where we have actually said that okay, I can live with whatever state I have. I just want to rotate my MUB, my mutually unbiased basis, to the right setting to carry on with my experiment. So I change my measurement itself rather than change the state. And so that is an alternative approach. So, just to summarize again, it could become a longer conversation, but then there are many, methodologies that people are following to ensure that they, can either get back the original state by bringing about different kinds of rotations and so on, polarization rotations and so on, or live with that same state and change the measurement basis, which also works beautifully. So this, in fact, we have just done. So just we can discuss more if you, yes, sorry, yes, Prajwal.
My question is related to what Shantana asked. When you were talking about improvements, you mentioned that there was an improvement in the dark count and they had detectors with lower dark count. But I thought that PMTs only had a quantum efficiency of about 35%. So it was quite stunning that they could get results just with PMTs. And I would have thought that quantum efficiency, like Shantana said, improvement
in
was
fact,
more important.
I don't want to go back to, just maybe slight confusion. So the improved dark count was using APDs. So they were not PMTs. So that particular experiment, which is the, the one with the Zeilinger experiment, the first Zeilinger experiment, they actually switched from PMTs to avalanche photodiodes. So they have the lower dark count. No, dark count is also important. So see, when you are actually doing an experiment where you are measuring coincidences, you have the actual coincidences, but you also have what are called accidental coincidences. So these accidental coincidences are not obviously the ones that you are after. They happen because there are counts that are getting registered which weren't intended, let's say. Okay, so that can happen because of the background. It can also happen because of the detector's inherent noise. So if that itself becomes comparable to the signal, then it, you have to subtract off a huge number, and that leads to again loopholes, I would say, to keep the discussion shorter. But then the one that I showed you about the lower dark counts, that also is for an APD. So they used an APD with high efficiency, low dark counts. Is that, yes, Shoptarishi.
Okay.
Oh, sorry.
So for these experiments, you are using the polarization properties of the light. So does this polarization property has quantum nature, in the sense that is it real? I thought that even if you don't measure, if it has some polarization, it will be still there, like Einstein thought.
Yes.
So does this polarization property is real, or it has a quantum property?
So polarization is a property of the electromagnetic field, right? So so polarization per se, I won't want to say that it has become quantum because of its usage here. What is quantum is of course the fact that we are using correlated pairs of photons. So if a photon has a polarization and then I am doing measurement between pairs of photons which are correlated at birth, which is entanglement, then it shows up in their properties. And polarization has been a common choice for this. But just to elaborate on that, entanglement is not just between polarization degrees of freedom. You can have entanglement between other degrees of freedom also, like orbital angular momentum, for instance, or spatial degree of freedom. So there are different ways in which you can harness this entanglement. It so happens that polarizers and choice between transmission, no transmission, or orthogonal, these things are quote unquote easier to motivate and set up for decades ago, right? But now of course we have counterpart experiments using time, using space, using OAM, all these things. So it's not, so the choice of polarization is of course historic and remains very relevant even now, but it is more the fact that we have a correlated pair of photons which makes the difference. So if you had classical light, then it won't lend itself to the same violation. I mean, you'll easily get less than 2.
Just taking on with what Arun was asking, I mean, so these days you can also get, I know of experimenters who work with light where, there's some kind of
orbital angular momentum.
Yeah, so is that being seriously
Yes.
pursued as because that looked like a very
That was a very serious one.
thing from,
No, it is very important.
Because
And in fact, polarization is nice if you actually stick to a two-dimensional degree of freedom. But if you want to actually access the, the richness of higher dimensional quantum key distribution, which is a very vibrant area of research, OAM is a natural choice because it is actually infinite dimensional. And then you can truncate it to
OAM
different...
is the short form for
orbital angular momentum.
Yeah.
So and also one of the other things, Tarun, is that the this what should I say, these structured beams, for instance the donut ones, the ring shaped ones, they actually are also they're again, experiments have shown that the shape is retained better than a Gaussian. So if a Gaussian beam is propagating over a long distance, it can be amenable to more distortions, whereas a structured beam kind of, and that is what leads to the use of a Cassegrain telescope, so that you get the advantage of both while remaining in the qubit domain. But if we go to higher D, OAM is being done very successfully, orbital angular momentum, and there are experiments on long distance quantum communication using orbital angular momentum, especially from the Ottawa group. Yeah. No, I mean, she can't stop the current person. Yeah. Yes. Go on.
Now, so all these previous generation experiments, especially the ASPE type of, so those were done, if I understand correctly, without heralded sources.
Correct.
So, of course, there was lots of background photons which also participated in the detector counts, which
Absolutely.
had to be served.
Yeah.
So, can you comment how?
Yeah.
Because this is a
In
very-
fact, it is a very nice explanation in the second ASPE paper that I showed you, where they have, I mean, again, the devil is in the details, but I didn't want to go beyond a point in the actual presentation. But they have actually done experiments where they have, measured for only the background and subtracted those from the ones that they have measured for the actual settings, and it is the subtracted version that we see. Definitely. And in fact, even in these heralded photon type experiments which are now happening, although I agree that they are obviously more efficient, still we do background subtraction from, that is where this accidental came in. But for them, they actually did these auxiliary experiments I talked about. So some of them were just to, have an idea of these numbers so that they could subtract off, because there are many terms, right? Yeah. Thanks. Yeah. Yes, Raghu. Radio astronomy. Yes.
Okay. So, tell me, whether all coherent photons are entangled? Source
Are
of
coherent photons entangled? No.
Source of photons?
No.
No.
No. Oh, no. Of course, it depends, okay. So you have to be a bit more specific. So in which degree of freedom? So, maybe there is some entanglement. So first of all, you're talking about 2 photons, I hope.
No.
Or a single photon.
I'm referring to coherent distance in space, which we normally talk about in astronomy,
Yeah.
in while detecting it. Okay, how different is that from an entangled photons, which are even separated long distance, they do not lose their coherence.
Right. Well, so we're talking about single particle maintaining coherence as opposed to the coherence in a quantum property shared by two particles. So of course, the analogy will little bit end there in the sense that, a single particle which has a certain coherence, so you have a certain coherence length for the kind of these SPDC, this heralded photon sources that we are using, the coherence length need not be very high actually, so they are quite low. But then the entanglement coherence is different, so we have to be a bit careful here as to what we are really aiming for. But then just to interpret your question in the right way, the answer would be no. They are not the same.
Sure. Okay.
Okay, yeah, because one could elaborate later.
Any more questions?
Just as a common man, what is the impact of this technology? Are we going to live in a quantum age of computation or like internet age or something like that?
Yes.
And what are the fields, is going to have an impact?
So the last 10 minutes did not have any impact on you. So I will repeat it a little bit. So we are all common men and women, of course, yeah. So that's what I try to say, right? So why should we care? We have violated local realism. We have proven quantum mechanics is good. We have disproved local realism. All that is good. But why does it impact us? It impacts us because, of course, it will revolutionize how we communicate. Where the security in our communications will be far more because of these contributions. It will revolutionize the internet because we will have a quantum version of the internet. We will have quantum computing nodes which will be connected with a communication channel. That is what is called the global quantum internet. And of course, if you are, I don't know if you are a spy, but then if you happen to be one, then we can actually come up with unhackable random numbers so that you cannot succeed in your evil intentions. So it depends on what kind of common man you are, but then if you are, society friendly one, then you will benefit from these technologies, whether it's computing, whether it's communication, whether it's sensing. So, all this, so we have what are called quantum radars, quantum lidars, so then, you use entanglement again as a resource for improving imaging. If you are from the, military sector, then maybe we'll see enemy ships or enemy stuff better. So, the increase in sensitivity, increase in security, increase in computing power will impact us. Either as a whole or at least one of them. We cannot escape this. So we better accept it and understand it and go forward. But if you actually are anti this thing, then we will come up with ways to prevent you from hacking into our systems. Yeah? Yes.
Any more questions?
Thank you for the wonderful talk, ma'am.
Thanks.
So my question is with regard to local realism. So you mentioned that just from what you just earlier mentioned, violating local realism, right? That's what you mentioned. So I have always been perplexed by this. So does Bell's inequality address the issue of realism? I've also seen many papers that just say that it provides a proof of non-locality, but it still doesn't question still doesn't address the question of realism. So does it address both? Why do we see these two terms clubbed together?
See,
and
one thing is
said all along?
that so we have to understand that we are violating local realism means that we are actually satisfying the strong locality condition and violating the realism. So what are we doing? And of course, this is where we get into the territory where we could have longer conversations and steer away from experiments, but I know you have a philosophical mind, so let me try to address that question. So what do we mean by violating local realism? Is, of course, first thing we need to ensure is that we are not, dealing with things which are not, local, which don't have the locality loophole. All those discussions we went to is to ensure that our experiments, not my experiment, but the experiments which have happened, are actually satisfying Bell's strong locality condition. What is Bell's strong locality condition? It is Einstein, the special relativistic locality plus the fact that my, measurement setting should not affect your result. which means I should not be able to do something and quickly send you something so that you can alter your result. So this is also important. So it's not just, so there are other things, called predictive completeness. So predictive completeness plus Einstein separability gives you Bell's locality. We can discuss the math behind this. I actually can show you the math. But having said that, once you do that, then if you are violating Bell inequality, then the thing that is left to violate would be realism. Because that is an assumption. These are the two assumptions, right? So if you're satisfying one and you're violating the whole, then clearly you're violating the second assumption. And we went through the CHSH derivation, which showed you how that is an assumption, because if this pre-existent property did not exist, I can't say that I'm measuring A0 to be +1. That is how we started. So indeed, that is what this is doing. But we can discuss more. I do remember you. So yeah, Shayantan has a question again. Yes. Sorry. Yeah, it's out of our.
Oh, it's okay. I can ask later.
No.
Yeah, so you spoke about this entanglement between different degrees of freedom, and some of them. So has it been shown explicitly that suppose let's say pair of entangled photon, like 1 degree of freedom, like polarization remains entangled, whereas like due to decoherence some other degree of freedom has been. So then after that, like, do you call...
That is why I said that they have shown that polarization is robust. But then, to be able to actually do measurements which cater to many degrees of freedom, of course, if you are going to use polarization as your experiment, then you will set up your experiment to measure the polarization projections. So if you want to also do, let's say, something else, then it becomes quite challenging to do all sets of measurements in the same experiment. But people have dealt with what is called hyper-entanglement, which is not, hyper in the sense that, it's more than 1 degree of freedom. And so, of course, in fact, I do not know whether they have been able to show that it remains in one and not in the other. That's something I can find out and let you know. Yeah, but then it's quite tricky though, because you're setting up your experiment for 1 degree. So, but then there are experiments on hybrid and hyper, which will lend itself to such investigations, right? Yeah.
Thanks.
Thank you, Shantan.
We can carry over the questions to the tea outside. So we thank once again Urvashi for the very nice talk, and there were a lot of questions. So I would invite our director, Professor Tarun Saurdeep, to give a token of appreciation for Urvashi.
Thank you so much. Yeah. Thanks a lot.
So
Oops.
I should mention that this is all part of this Vignyana Kathegalu, which is a new initiative of public lectures, and I'm glad that the Nobel Prize lectures are becoming part of it, thanks to the people who are organizing the Vignyana Kathegalu, and given the response, I think it's a great way forward. So we should use this public lectures for celebrating science in many ways. Thank you.
Thank you very much. Thanks.
Thank you all for coming. Please join us for the tea outside.
Stop, that's it over. It will get automatic stop, or you should stop manually. We can call him. रोज मार बिಟ್ಟು